Hi everyone. We are going to present a paper on joint rank 1 matrix completion and automatic rank estimation via L1 norm regularization. Before entering into the algorithm, let's understand the problem of matrix completion. Completing a matrix from a small subset of observed entries is framed as matrix completion. In the image left hand side, we can see that the matrix is only partially observed. The places with black circle represents that the entries are observed. Entries with question marks indicates that it's not observed. Matrix completion task is to interpolate the missing values using a proper prior to the problem and observed values. The major application we are targeting is image inpainting. Image inpainting is an artistic term for image interpolation. Image inpainting is the process of restoring the lost or deteriorated part of an image. An image is nothing but a rectangular arrangement of pixels and hence it's a matrix of numbers. So we can treat the damaged part of the image to be missing parts and treat it as a matrix completion problem. Here we see the applications of image inpainting. Image A describes the problem of wireless image transmission. If the image is transmitted wirelessly, there is a possibility of image packets getting corrupted in the channel and hence some part of the image gets corrupted. We can conceal the error incurred due to transmission using matrix completion to interpolate the missing parts. Image B describes the problem in preserving paintings. In ancient photos or paintings, corrosion due to a variety of reasons makes the painting incomplete. We can use matrix completion to interpolate over the damaged or missing parts of the image. The last image covers the cases where the image is corrupted by some other image or text and can be removed as shown using the same procedure. Other than these, matrix completion finds its use cases in collaborative filtering, global positioning systems, and machine learning. Here we formulate mathematically the matrix completion problem. Let M be a matrix of dimension I1 cross I2 with partial observations in an index set omega. Omega is a binary matrix of same dimension as M with ones in places where the entries are observed and zero otherwise. P omega denotes the associating sampling operator that acquires the entries indexed by omega. So we can formulate like this. Minimize some function of x, as in do something that enhances the quality of restoration, subject to the condition that the matrix entries that were observed are preserved in the completed matrix also. That's what this line is stating here. Before completely formulating the matrix completion objective, let's understand images. Images are generally high-dimensional data points and pixels are highly correlated. Therefore, they are generally low rank and lie in a low-dimensional manifold. Images are represented using a matrix with low rank. That's what this picture here is stating. Therefore, in the case of images, we need a matrix with minimum possible rank that satisfies this constraint. You would have guessed the function f by now, which is a rank of x. So you need to minimize the rank of the completed matrix subject to the condition that the observed pixels are preserved in the completed matrix x. But rank is a non-convex and combinatorial function in nature and hence optimization will become very difficult. So we need to find a convex relaxation for this problem. There are two main approaches to this problem. The first one being nuclear norm minimization. Nuclear norm of a matrix is the sum of singular values of the matrix. Since it's a norm, it obeys triangle inequality. Moreover, it's a convex function and it turns out to be the tightest convex envelope of rank of the matrix. Now, instead of minimizing the non-convex rank function, we can minimize convex relaxation of it, which is the nuclear norm of the completed matrix, subject to the condition that the observed values are preserved. The other one is using low rank matrix decomposition. Any matrix of rank R can be modeled as sum of R rank 1 matrices. Assuming that the rank of the completed matrix is R, we can decompose the completed matrix as UV transpose as shown in the slide. Now we need to minimize the Frobenius norm between Z and UV transpose. Z is a matrix of the same dimension as M, but observed entries are preserved, which we can see from this constraint here. So in order to guide the optimization algorithm to preserve the previously observed matrix entries and not to deviate much from it, we need this kind of formulation. We can take either UV transpose or Z as the output. We will get a clear understanding once we go into the algorithms. As we have seen, any matrix of rank R can be written as weighted addition of R rank 1 matrices. The collection of all the weights is called the weight vector and U and V matrices can be inferred from the formulation here. Isn't this quite similar to SVD? SVD is a special rank 1 decomposition in the sense that U and V matrices are orthogonal and all the weights are singular values of the matrix and hence they are non-negative. How can we get the rank P approximation of a rank R matrix using SVD? For that, we take the help of Eckart-Young-Mirsky Theorem, which states that given a matrix M with rank R with singular value sigma 1 to sigma R, the optimal rank P approximation of M is given by its truncated SVD representation as is shown here. Note that SVD is a special rank 1 decomposition. The theorem basically says that the rank P approximation is obtained by adding rank 1 matrices corresponding to the top P singular values. It turns out that the matrix is also the solution of this optimization problem. Out of all rank P matrices, the matrix which minimizes the Frobenius norm with M is this truncated matrix. Now let's find out the minimum possible value of this objective function. Frobenius norm of a matrix is the sum of squares of individual entries of the matrix, which is equal to the trace of M transpose M, and it turns out to be equal to sum of squares of singular values. Taking the trace of M transpose M and substituting the SVD of M in the expression and simplifying it using the trace operator's properties, we end up with the above relation as shown in the slide. Now taking the Frobenius norm between M and the truncated SVD representation of M and following the steps, we end up with Frobenius norm square equal to summation of squares of leftover singular values. Here we formulate the optimization problem of matrix completion using rank 1 decomposition. Let Z be the completed matrix which we require. Take another matrix X of the same dimension as Z but always consistent with the observed entries due to the constraint which is shown here. You also want the matrix Z and X to be near in Frobenius sense. Also note that Z's rank 1 decomposition can be written like this and hence its rank is R. So minimizing the norm, we ensure that the completed interpolated matrix doesn't deviate much from the observed entries. Also note that we have fixed R here, so we assume that we have the knowledge of the true rank of the matrix. While solving for the problem, using this algorithm, we need to apply SVD for every iteration and hence it turns out to be slow in practice. It also has no parameter to tune like step size, so it's easy to implement. But if R is not close to the true rank, it might not perform well. Here we will see how we can estimate the rank automatically unlike R1MC where we assume the rank. This is similar to R1MC with an extra L1 norm regularization on the weights vector. And also we have R in the minimizing target, which means we will be finding the rank in the due course of optimization. We all know that the number of non-zero entries in the weight vector decides the rank of the completed matrix. Mu is called the regularization parameter, which essentially weighs the L1 norm regularization objective. The greater this value, more sparse the weight vector becomes. So it's a trade-off between good reconstruction and low rank. By adding L1 regularization, which promotes sparsity, we can selectively find out the optimal rank of the matrix by analyzing the final weight vector, which will be sparse. This is to give a high-level overview of optimization of L1MC. Here we define the target variables, which are the weight vector, U, V and X. We divide the target variables into R plus 1 subblocks, which are W1, U1, V1 to WR, UR, VR and X. We optimize one subblock of variables while fixing the other subblocks and repeat this until the convergence is reached. Here, these are the update equations we get when we write the Lagrangian in terms of the selected variables and solve them. I would like to draw your attention towards the weight update where you can see the effect of L1 norm regularization. There is a region where the weight value goes to 0 if the trace of the matrix shown here lies in this range. This can be derived when Lagrangian is solved for the weights. We have implemented R1MC algorithm in Python using NumPy and we are presenting you the results. Here is the incomplete image with 50% of the pixels blacked out. Here is the completed matrix using R1MC, assuming the rank to be 70 for a 720 x 720 image. The last one is the true image and we see the reconstruction is quite accurate. Thank you for listening.